Hmm.
गुड मॉर्निंग मैम।
गुड मॉर्निंग। कौन बोल रहा है?
मैम एलिया।
Yeah, how are you?
फाइन मैम, हाउ आर यू डूइंग?
I'm fine, thank you. Hello, Amna.
Assalamualaikum, ma'am.
Walaikum salam. Hello, Aruba.
Hello, ma'am.
Hello, Halima.
Assalamualaikum, ma'am.
Walaikum salam. Hello, Raiba.
Assalamualaikum, ma'am. How are you?
I'm fine. How are you?
Good, ma'am. Thank you.
Hello, Mahmood.
Assalamualaikum, ma'am.
Walaikum salam. Hello, Nashra.
Assalamualaikum, miss.
Walaikum salam. Okay, so let's start. Okay, so today we are going to talk about waves, right? Can you see the chapter I've shared with you?
यस मैम।
Good. So I would like someone to tell me what you understand by waves. What are waves? Yes.
आमना महम मैम जो लहर होती है लाइक लाइट की वेव्स हो गई और एनर्जी वेव्स हो गई इस तरह से
Okay, Amna Maham. Okay. So Amna Maham says that an example of waves can be light waves, right? That's what she said. So yes, so she gave an example of light as a wave. Would someone else like to add something? Yes. Yes, please. Give me an example of waves. Tell me something you understand about waves. Or is light on the only kind of wave we have?
Ma'am, Aruba Rayas.
Aruba, yes.
No, there are sound waves as well.
You have sound waves.
And like
Sound waves.
a wave is like caused by a disturbance from the normal level.
Okay, good. So Aruba, you okay? And someone else who would like to give us some more information?
Ma'am, we have water waves too.
Better now.
Amna here.
Amna, water waves. Okay, you can have waves in the ocean, waves in the sea, waves in the even like if you have a still water in something, it's a pond or even a vessel, and you throw a stone inside and you will see the ripple effect going out, and that's also an example of a wave, right? Okay, yes, anyone else? Some other examples, some other information you remember? And one of the purposes of waves is to carry energy from one place to another, like, sound carry is a form of energy, light is a wave, is a form of energy, right? So we'll go from here, and you have different descriptions like waves as a transfer of energy, right? It's a disturbance. Somebody also talked about disturbance. There are different kinds of waves depending on the nature of the wave and the medium. For example, we have mechanical waves. Mechanical waves are defined as a kind of wave that require a medium for propagation, okay? So, whereas electromagnetic waves do not. So which one are mechanical waves and which one are electromagnetic waves? This chapter will help you understand that. And then we have the concepts of waves related to displacement, amplitude. These are some terms that we come across: period, compression, rarefaction, crest, trough, transverse, longitudinal, frequency, wavelength, and velocity. So these are some terminology, some concepts related to this. And then the relationship between the energy that is being transferred and the direction of motion. And then, of course, the relationship between the velocity of the wave, the frequency, and the wavelength. Similarly, as one of you gave an example of sound, sound waves are vibrations or oscillations of particles in a medium. So if something vibrates or oscillates, it produces waves. So this is an example you can see here. This is, for example, if you take a string or a rope, you fix it at one point with something, and you take the other in your finger in your hand, and then you move it up and down, you will see that such a pattern of waves is formed. So this is also an example. In this case, what is happening is that energy is moving up and down the string, and but the particles of the string, which you may say are the atoms or the molecules of the string, they will remain in their positions. They are not going from one place to another, but energy is traveling along the wave. So here you can see again an example of a wave, in which case you can see that a wave has a sinusoidal shape. Sine is a trigonometric function that you must have studied in maths in school. And when you plot the sine wave on a graph, you get a shape that is like this. So this is known as a sinusoidal wave. So in this sinusoidal wave, the top part is known as the crest. So, and the bottom part is known as the trough. So when a wave is moving and you take, let's say, a photograph at different time intervals, this is at t is equal to 0 seconds, t is equal to 5 seconds, t is equal to 10 seconds. You will see, if you start observing one particular point and you follow it in these photos, you will see that the position of this crest changes here. So you can see that this position was here and now it's here. So there has been a displacement, a movement towards this direction by a certain distance. Okay. Now again, after a certain time period, you again observe the same point. You will see that this crest has now moved further. So you will see that this is again a displacement. Now you can establish a relationship between time and displacement, for example. So energy transformations in communication systems, you are using communication systems all the time. Like right now, we're using the internet, right? To take this class, to take this Zoom meeting. You're using your smart devices, your smartphones, you are using communication systems all the time, So modern communication devices involve such energy transformation, right? And hence the concept of waves is very applicable. So for example, what is a microphone? We are using a microphone right now. So you can hear my voice because I'm speaking into a microphone. So what does a microphone do? When I'm speaking, the the kind of energy that I am producing is sound, right? But then this is changed into electricity, and then this is carried and over optical fibers, let's say, and then you are able to then your device will take this electrical signal and convert it back to sound signal, and that's how you hear my voice. So this is an example of energy transformation using waves. Okay, so energy transformation of a mobile phone are identical to those of a radio, and so on and so forth. So it's the same concept that previously in older let's say a few years back, a few decades back, people were using radio, but the principle was the same. Now we're using mobile phones for the same purpose, right? Now these are different examples where you can see the transformation, the energy transformations that take place, right? So here you have the examples of, let's say, the fixed telephone. I don't know, nowadays we are mostly using smartphones, but we also have fixed telephones in our homes and offices, and they use the same concept. Somebody speaks into the microphone, which is sound, and then this is converted into electrical energy, and this electrical energy travels over a distance, over wires or fiber optics, and then it is again converted into sound so that you can listen to it. Again, the radio and the mobile phone are also using, this is a radio transmitter, radio waves transmitter, and you can see that sound converted into electrical energy, it's then goes through the radio waves transmitter, which then again, this is the principle of the radio. So it again converts it into electrical signal, transfers it to another place, and then there's magnetism involved in your speaker, and then you get the sound at the end. The fax machine is also an example in which fax, you scan the page, the letter, whatever you want to send with light. Okay, so that is light energy, which is then converted into electrical, and then there's also heat, and heat is also a kind of energy, and in the end, the person who receives it again gets it scanned in the form of with light, and then it's printed out. So computer is also a similar example. For example, when we type on a keyboard, when we are typing, this is an example of mechanical energy. This energy is then transformed into electrical energy, which then, for example, if you're saving this on a disk where this is magnetic energy, and then it's transferred back into electrical, and then on your monitor you see it as light. So these are different examples. Okay, so now classification of waves. We've talked of waves, the concept of waves, and how it transforms energy from one form to another. Now there are different kinds of waves, and we can classify them on the basis of different properties that they have. And for example, one class of waves we just saw was mechanical waves, right? So mechanical waves are what kind of waves? How we define mechanical waves? How do you define mechanical waves? Yes. So mechanical waves are waves that require a medium for their propagation. You see, they need a medium. Medium means, for example, can you hear sound in vacuum? Do you understand what medium means?
Yes, ma'am.
Who's speaking?
Sahib.
Can you give me an example?
No, medium ka, like the medium through which we are speaking is, let's say, headphones.
No, this is not a medium.
Wire.
No, this is headphone is not a medium. Medium.
So this wire connection is.
Huh?
This wire that transmits my sound.
No, look, when I am
through...
speaking, the medium that carries my sound, initially the sound waves travel in air. Okay, so air is the medium in this case. Okay, so you might also know that, for example, you can hear a voice across a wall, then the wall will be the medium. Okay, so that's you're talking about the devices. Headphones are devices. Okay, So mechanical waves are waves which need a medium to travel. And for example, sound is an example of a mechanical wave, and it needs a medium to travel. And if there's no air, for example, if there's vacuum, you will not be able to hear the sound. Okay, so if, for example, someone is speaking in, let's say, in space, you will not be able to hear when there is a vacuum. But light, on the other hand, is an example of an electromagnetic wave. Electromagnetic waves do not need a medium for their propagation. So this is the main difference in this case. Mechanical waves further have types. We have transverse waves and we have longitudinal waves. So transverse waves are defined as waves in which the particles move up and down across the direction of motion of the wave. For example, if the wave is going towards the right, like this, the particles are moving up and down, up and down, up and down. The particles, the direction of motion of the particles, of oscillation of the particles. The particles are not leaving their position, but they oscillate, they vibrate up and down, and is perpendicular to the direction of motion or propagation of this wave. So this wave is defined as a transverse wave. Okay, so the vibration in a string on a musical instrument, for example, is transverse. A water wave that we just discussed can be an example. And then we also know that electromagnetic waves are also a form of transverse wave. Longitudinal or compressional waves are waves in which the definition is opposite to the one for transverse waves. In this case, the particles vibrate along the direction of motion of the wave. So if the wave is going towards this direction, the particles will also vibrate in the same direction. So this is known as a longitudinal or compressional wave. And the example for this is a sound wave. Okay, so here you can see in this figure, in a transverse wave, the particles move up and down across the direction of propagation of the wave. So the wave is going here, it's moving towards the right, but the particles are moving up and down, and you can see that this is perpendicular to the direction of propagation. Hence, this is an example of a transverse wave. Longitudinal or compressional waves are described with the example of a spring. You can imagine a spring. For example, when I'm speaking in the air is what? It's a combination of molecules, right? So when you speak, the molecules are pushed together. When they're pushed together, this is called a compression. And then when the sound lowers, then they expand the distance between them, and that's known as a rarefaction. It's similar to spring. When you pull a spring, that is called a rarefaction. And when you push a spring, the distance between the different parts of the spring becomes closer. That's known as a compression. So you can see that part of this, let's say if this was an example, so part is this part, the dark part that has been here shown here is the compression. And as the sound moves, for example, this compression moves through the medium, which may be air, for example. So you will see that the compression was here in the beginning. After some time, the compression is here. After some time, the compression is here. So this is an example of a longitudinal wave traveling. So you can see here we have the examples of loudspeakers, which is again producing sound, and we have the example of earthquakes are also a kind of a wave. And here you can see the loudspeaker. These are the compressions that are traveling, and then later on this is the human ear which is receiving this sound. And this is a earthquake in which you can see that there's a seismic compression that is transferred across the earth, and then you see that there's the explosion or the earthquake, and which also produces sound. So there are some other kinds of waves also, for example, torsional disturbances. So groups of particles twist backward and forward around the direction of motion of the wave, and this is called a torsional wave. But we mostly talk about transverse and longitudinal waves. Now we talked about electromagnetic waves and gravity waves. Electromagnetic waves, the example I gave you was light. For example, light, radio waves are also electromagnetic waves. Microwaves are also electromagnetic waves. X-rays are also electromagnetic. So it's a whole spectrum that comes from the sun. And gravity waves are also another kind of a wave, as you may remember if you're interested. There was a lot of news of the Nobel Prize that was given for the detection of gravitational waves. Gravitational waves was something that has been theorized since several decades, but it was recently experimentally detected. And also there was a Pakistani scientist also who was involved in this project. Her name, you may be familiar, is Nargis Mevlala. So there are a lot of interesting videos you can see on the internet about this. So anyway, electromagnetic means the word electromagnetic, electro for electricity, right? It's electrical charges, okay? Magnetic means it's related to magnetism. So these are waves that, in which a positive or negatively charged particle is affected by changing the electrostatic or electromagnetic fields. So these are vibrating electric and magnetic fields within these within the electromagnetic spectrum. Moreover, we can create a disturbance in a group of charged particles simply by moving some particles. So this motion creates a varying electromagnetic field which moves outwards, and hence you have these waves. So electromagnetic waves vibrate in 2 dimensions and travel in a 3rd dimension. So you have X, Y, and Z axis, and the 3rd axis is the Z axis, but we cannot properly draw it here. It's perpendicular to the plane of this paper, right? It's perpendicular in this case, and therefore the oscillations of the electric and magnetic field will be perpendicular to each other. So one will be, let's say, in X, the other in Y, but then the direction of propagation will be along the 3rd direction, which is perpendicular to these directions. So X-rays, I just gave you the example of X-rays, light waves, heat radiation, radio waves are all examples of electromagnetic waves. And these are waves that can travel through vacuum. Just as I said, mechanical waves cannot travel through vacuum. They need a medium, and medium can be air, it can be water, it can be a solid. But electromagnetic waves, these are the waves that are coming from the sun, and they can be transmitted through vacuum. They do not need a medium for their transmission. So again, gravity waves, which is a very interesting concept. Gravity waves is something that has to do with mass. We know that if we move mass anywhere in the universe, that motion will have an effect on all other masses in the universe. So this is again a very interesting thing. You must have seen it. So in this case, you see that waves are produced, which are known as gravitational waves. So these waves would cause other masses and their paths to vibrate. And in this book, it's written that attempts are being made to detect it. But recently, there was a Nobel Prize, because this book is older. And there was a recent Nobel Prize. What was the exact year of that prize? You can check it up, in which these gravitational, maybe 2017, I think. You can check it out. So in which gravitational waves were detected. So it's an interesting experiment. I can also post some videos for you when we study this topic in detail. Okay. So seismic waves, sound waves, and water waves are mechanical waves. Okay. Here are the examples of, okay, because they all travel through a medium. So if they are mechanical waves, they're called mechanical waves because the energy that's associated with these waves passes from particle to particle within the material, and this material is the medium, right? And hence they require a medium. Okay. They cannot travel through vacuum. You cannot hear sound if there is vacuum. There have been very simple experiments that people have done. For example, if you have a jar and you create vacuum inside and you place a bell inside and you try to switch on that bell, nobody will hear the sound. So this is a proof that it does not travel through vacuum. So the material, the medium that we are talking about can be a solid, it can be a liquid, it can be a gas. Gas means it can be air, for example. When we're speaking in the room, there is air. So air is the medium that's carrying our sound from one place to another. Okay. So again, gravity waves results from rapid changes in position of massive bodies. There's Newton's laws, and then there's Einstein's concept of space and time, and these are related to that. We'll study these later. So these waves are also transverse and like electromagnetic waves, and they do not require a medium to propagate. So wave terminology. Now, as I said, there are important terms that we use when we're talking about waves. So one of the terms is a crest. The other term is a trough. So I just talked about it when I was explaining this. So if you look at the sinusoidal wave, then the maximum position is known as a crest and the minimum position is known as a trough. Okay. And then we have the equilibrium position. The equilibrium position is the position at the origin normally. Okay. The point where there's the body does not move. Okay. Or it's also known as the rest position. And the cycle, and then there we have the term cycle. Cycle means it's a repetitive motion. So if you see the motion from here to here, for example, this is one cycle, and then it repeats the same again. This is two cycles, and so on. It's a cyclic motion. Another term that we talk about is amplitude, right? Amplitude of a wave is the maximum displacement on either side of the equilibrium position. So particles in the path of a wave oscillate positive and negative displacements. Again, when we look at this like this, so the maximum distance from the mean position, this or this will be the same, and this is known as the amplitude, and it's represented by capital A. The symbol is capital A. So waves carry energy from their source to particles. We just talked about this. The energy transported by the wave is proportional to the square of the amplitude of the wave. So this is an important formula. You may need this formula to solve some problems like this given over here. Okay. So wavelength. Another term that we talk about is wavelength, lambda. You're familiar with this. So lambda is a symbol that is for wavelength. And how do we define wavelength? The wavelength is defined as the distance between adjacent crests or maxima. Crest can be called a maxima also. So it's a maxima point of the wave, and or between two adjacent troughs as well. Okay. So you can see in this case that this is one crest and this is one crest, and the distance between them will be known as one wavelength or one lambda. Or you can take two troughs. So the distance between these two troughs, adjacent troughs, will be called a wavelength lambda. The displacement, of the particles, these are all displacements. So it starts from 0. 0 is the equilibrium position, and then there are different displacement, and the maximum displacement is 10, which is the amplitude. So A amplitude is the maximum displacement from the mean position, which is 0. So it can be upwards or downwards. It's the same. The value remains the same. The cycle, as I said, this motion from here to here is one cycle, and then it repeats itself, and this is called 2 cycles and 3 cycles and so on. You can see that lambda is also marked over here. So this diagram is important to understand the terminologies that we've just talked about. Another terminology is period. And when we're talking about period, in some books, this is also written as time period. The time period, and the symbol is capital T. So you remember that the symbols is not small t. We've used small t for time, but that was just time. This is a particular term which is time period, and this needs the symbol capital T. So this is defined as the period of a wave, which is the time taken by a particle to complete a single complete cycle. So the time required to go a complete cycle for a body is known as the time period. And you can also measure this time. Of course, we have experiments, like you will also perform an experiment, for example, of a simple pendulum. A simple pendulum is also an example of a oscillatory motion, vibrational motion. So this is the mean position, which we are also calling the equilibrium position. This is the extreme position, and this distance between the mean position and the extreme position is called the amplitude. And the time taken, okay, for one complete cycle is the time period. So normally in this experiment, we give you a stopwatch and we ask you to measure the time period. So, Okay, right. So I would like you guys to practice this today. And also last time I sent you the lab material and your homework was to practice that. So your homework today is to practice what we have studied in class today. Okay. So
Yes, ma'am.
yes, please do that, because if you do like if you sit for 1 hour in the evening and practice what we've done, you will not have a problem later on. Okay, so I just wanted to show you something. Let's see. Yeah, so right now I want you guys to solve this 2.6. नहीं बल्कि ये वाली ना करो. There was another one. Let's do another one. Wait, I saw another one. Where is it? अच्छा ये वाला करो. Let's do 2.6. Okay, so I would like you guys to do 2.6 and whoever does it will get a point. And meanwhile I'm going to take your attendance. So everyone is there. There was one student who came late, and so I'll just call out your names. Ahmar Fahad is not here. Then we have Aisha. No, she's not here. Ali Musa, no. Mahnoor.
Yes, ma'am.
Good. Nimra. Nimra is there. Nimra. Maybe she logged in and then I don't know where she is. Okay, so Nimra is. We don't know what she's doing. Okay. Asad, Sayyid Azad Asad, Farooq, Muhammad Ahmad Farooq, Awais Khabar Gill, Laiba,
Yes, ma'am.
Sahib.
Yes, ma'am.
Okay, Elia,
Yes, ma'am.
Amna. Amna,
Yes, ma'am.
yes. Nashra,
Yes, ma'am.
Aruba,
Yes, ma'am.
Halima,
Present, ma'am.
Nawab.
Present.
Nawab, you were late.
Ma'am,
And-
internet.
Okay,
Yes,
Sumavi
yes.
and Saul Rafaqat.
मैम
Who is this?
मैम निम्रा मेरा माइक अनम्यूट नहीं हो रहा था, मेरे लैपटॉप में प्रॉब्लम हो रही थी. आई एम सॉरी.
Okay, चलो ठीक है. Okay, right. अब कौन बोल रहा है? Okay, now we go back to the question I just gave you, and who would like to solve this? Like you can each solve one part. So just tell me your name and we can talk about it.
Ma'am, the amplitude of the wave is
What's
2
your name?
centimeters.
Just a moment. What's your name?
Laiba.
Laiba. So Laiba says that the Laiba ऐसे लिखते हैं ना, Laiba is amplitude is equal to
2 centimeters.
2 centimeters. Do you all agree with this? From this figure, the amplitude is 2 centimeters?
Yes.
Or does someone have a different answer? If you have a different answer, you can tell me. Okay, who would like to answer the next one? The wavelength of the wave.
Ma'am,
Okay.
Aruba.
Aruba, yes, what's the answer?
4 centimeters.
4 centimeters. So lambda is equal to 4 centimeters. Okay. So Aruba, your name was Aruba, right? अभी
Yes.
किस Aruba इतना ऐसा बोल रही. Okay, so Aruba gets 1 point. And what is the period of the wave? Who will answer this one? And what is the velocity of the wave? The last two parts. So in order to answer this, you will have to study this, okay? Here, we have talked about frequency here, okay? The amplitude and period of a wave, we talked about this. Then frequency is the next thing. So frequency is defined as F, and It is the inverse of time period. This is the formula. Frequency is the inverse of time periods, and the units are either second inverse or hertz. Okay, so the SI unit is hertz. So this will help you understand this the question I was just asking. And then for another question, what you need is to know the formula for the wave velocity. The wave velocity is defined as the speed at which the disturbance moves through the material. It depends upon the kind of wave, the type of material, its density, and the equation is this: V is equal to lambda f. And if you put f is equal to 1 over t, then the formula is V is equal to distance traveled divided by time. So this is, again, you get this formula. So these are the formulas you need in order to answer the next part. So now we can go and answer this. So who will tell me the answer for the period of the wave? The period of the wave is you know that the next your quiz is on when do you have your quiz? Hello, are you following the assessment plan that we decided? The quiz, your quiz is on 29th March. Okay, so 29th
Yes, ma'am.
March is a Monday. Okay, so on Monday during class time you will have your quiz. Okay, and the quiz will be open for a short time, shorter than the assignment. So be ready, prepare yourselves for the quiz. Okay,
Yes, ma'am.
so I can share this with you.
Ma'am, can you repeat the syllabus of quiz?
The syllabus is chapter 1 for the quiz, because chapter
Okay, ma'am.
chapter 2 we can add chapter 2 also. Do you want me to add chapter 2? Can you see this board that I am showing you?
Yes, ma'am.
Yes, ma'am.
So this is chapter should it be chapter 1 or both chapter 1 and 2? Sorry. We'll decide this. Okay, so you keep preparing yourself. Okay, so this is the quiz.
Okay, ma'am.
On 29th March, that is due on Monday during class time. During class time, it will be on Moodle, and you will have a limited time to do this. Okay, so please make sure that you have internet or data package, whatever you're using, and also your device should be charged. Okay.
Yes, ma'am.
Okay, good. Okay. So for your homework, prepare quiz, study, and practice chapter 1 and 2, and also practice lab material. Okay, so remember to follow up on your lab also, because this is a your quiz is on 29th March during class time. It will be open for limited time.
It's on Moodle.
Yes, on Moodle.
Ma'am, quiz will be same like assignment, was MCQs placed.
Similar, yes. ठीक है?
Okay, ma'am.
Okay, take care. Bye.
Okay, ma'am.
Yeah.
Allah Hafiz. Take
Allah
care.
Hafiz. Allah Hafiz.